Hi, everyone. Welcome to this first walkthrough tutorial on how to use the mvgam package. So my name's Nick Clark, and I'm the author and maintainer of the mvgam R package, which is a package for fitting Bayesian state space models, initially designed for time series modeling, for dealing with time series that might be kind of challenging to model with existing software in R. Especially if you have missing data or observations that are not don't meet all the assumptions of most time series modeling software. So the purpose of this tutorial is just to introduce you a little bit to the package, how it works, some of the functionality that can be used with the package, and then how you can fit models and then do some post-processing of those models to understand a little bit about what the model is trying to tell you and how it might generate predictions, and then use models for forecasting. So what we're going to do is walk through some simple examples of fitting a couple of different models to a count-valued time series. So these are non-negative discrete integers, which can sometimes be hard to model with other types of software. And what I'm going to do first is just show you how to get the data that we're going to use, which is an openly accessible time series data set. And then how to inspect the data a little bit to understand a bit of some of the features of this time series. Adding some Fourier terms, which is a very common approach to try and deal with seasonality in regression-based time series models. And then walking through a couple of different types of time series models. We'll spend a bit of time talking about Gaussian processes and how they can be really useful to model sort of long-term nonlinear trends in time series, as well as some other models that we can use as comparisons, both with fixed and time-varying seasonality. And then I'll finally wrap up by showing how you can create and evaluate forecasts from mvgam objects, and how you can even combine forecasts into an ensemble forecast if that's something you're interested in doing. Okay, so the first thing we're going to do is just load the libraries that we need. So I'm using the latest version of mvgam, which at the current time point, December 2024, is only available on GitHub. This will make it to CRAN probably early 2025. So this is version, what version is it? Let me check. Always worth checking. Yeah, 1.1.4. Okay, and you can download that if you're following along right now from GitHub. It just has a few new bells and whistles that aren't available in the CRAN version yet. Okay, I'm also using some common packages for manipulating data, the dplyr package, which is very, very widely used for lots of manipulations. And mvgam can make use of the marginal effects package, which is incredibly powerful for understanding effects that are that your model is estimating. So regression models can estimate lots of different types of complex effects, not just linear effects. But when we take into account link scales and other kinds of things that are happening, you can get lots of effects that are really difficult to interpret by just looking at tables of coefficients. And mvgam is a package that can fit generalized additive models in a state space form, so we can handle really complex nonlinear effects and multidimensional effects. And so using marginal effects as a way to help interpret these things is a really valuable add-on that the package can do. Okay, most of my plotting is done with ggplot2, so I'll load that. I also load the Gratia package maintained by Gavin Simpson, which is a really handy package for visualizing GAM objects, and that can also work with mvgam objects. And then a couple of other packages as well for better plotting and variable naming. So I'm just going to load all of these. Hopefully you can see my screen well enough. I'll focus mostly on the top left one here, and less so on the other panels. But I'll just try and move things around so that hopefully you can maximize visuals that come up. We do a lot of visuals when it comes to modeling time series. And so visuals are really important here. I'm just also setting a ggplot theme that I like to use just to make cleaner plots. Obviously, that's optional. Okay, so the next thing to do is to download the data. So I'm working with a data set of Campylobacteriosis counts from the TS count package. This is a data set that's openly available from the TS count package, which is another package in R for fitting time series models to non-Gaussian data, so particularly to counts. So that's a really good one to have a look at as well as an option for modeling time series. So you can see as it's come in as an actual time series object in R. So if I have a look at that, we can see that it's a class TS. It's a time series object, and it's a time series of 140 observations. Okay, so I'm just going to put that into a data frame and give it a time variable to make it a bit easier to plot with ggplot. mvgam is very similar to mgcv or brms or a lot of other regression modeling packages that you can use in R, in the sense that it likes to have data frames of data or lists, list objects. So it doesn't just widely, directly accept time series objects like some other forecasting packages do, but it's generally easy enough to put those into a data frame. So if I put those into a data frame here, and I'm just using a column called count as the actual values of the time series, which are counts of cases of this disease over time, I think over 28-day periods. And then a time variable, which is just an evenly spaced index of time. I'm not worried about the actual dates themselves. It's just each of these time points is evenly spaced, and that's all we need to worry about for this example. I'm also going to plot the data. So I use ggplot to just plot the actual time series itself and give it some labels and some colors, and then plot a histogram of the counts as well, just so we can see some of the features of the data. And then I'm using wrap plots from the patchwork package to put these two together. So here you can see, I'll just zoom in on that. You can see some of the features of the data. It's clearly a count valued time series based on the histogram. We're not seeing too much in terms of a big tail or a big skew in this distribution. So maybe a Poisson distribution would be good enough to fit these data, or possibly a negative binomial. But you can see here, it's got a sort of autocorrelation happening, but also a long-term kind of nonlinear trend that's been happening over the course of this observation period. So a really useful type of time series for showing off what mvgam can do, because again, modeling this type of data with a lot of existing packages is a little bit challenging. It's got low counts in some of these time points. You've got maybe some overdispersion happening, and traditional time series models often can't deal with those features. We can also use mvgam directly. So mvgam has a function called plot mvgam series. So it'll just take a data frame that has a time variable in it, and you can tell it what the outcome variable is, and it'll just plot some features of the data to try and emulate a little bit about what we've done here, just for inspection. So often when it comes to inspecting time series, there are certain things we might want to look at. So what this function will do is give you a series of plots like this. Here's the actual time series again, same as we saw before, and a histogram again, but also we have an autocorrelation function for these data. Sometimes these can be a little misleading when you're dealing with non-Gaussian data. There's often observational error and things that can make these a little bit harder to directly look at and interpret, but they can still be valuable. We can see we've got these delays in autocorrelation as you move to longer lags, but there's also some stronger autocorrelation at lags of 11, 12, 13, because that's around the window of when they're gathering new data on these things. So there seems to be a clear kind of seasonal pattern here of about 1 year or so. I think there's 13 of these in a year, 13 observations per year on average. So that makes sense that we're getting a spike there. So there seems to be a seasonal pattern there. And we can see the empirical CDF as well, which for some people is a little bit easier to interpret than a histogram, but they're showing you similar kinds of information. Okay, all that's telling us is that we've got an autocorrelated count-valued time series, and it helps us to think about how we might want to try and model this, what kind of observation model we might want to use to do that. Okay, but because we see this kind of seasonal signal, seasonalities might be something we want to deal with, either through covariates in some way, if we think certain covariates that we have can explain that, like temperature and rainfall and things like that, or just by adding features, augmenting the data set using certain features to be able to account for seasonality. So a common way to do that with time series is to add what are called Fourier terms to the actual data, and these are pretty easy to add to time series objects using a function from the forecast package called Fourier, which is a really handy one. It'll just add different sine and cosine waves to the actual data based on the frequency of the data. And so you can select how many of those you want to add. I'm adding 4 here, so 4 sine and 4 cosine waves to these data. And I'll show you in a minute what those actually look like, and you'll see how they can be used to model seasonality. So what I'm doing here is adding new columns to my original data set called DAT, where I'm adding those Fourier terms. They originally come from this package, the forecast package. It's a wonderful package if you haven't used it for time series modeling, but it does add some kind of funky names from the Fourier terms, and so I'm just cleaning those up a little bit using the janitor package, which is another widely available package just for cleaning data sets and cleaning names. So when I add that, this has to work. The Fourier function has to work directly on the time series object, that original thing that we downloaded, which is that CAMPy object. So it's just the time series itself, and it has a frequency of 13. As I mentioned, there's 13 observations per year for this data set, and so it's going to use that to calculate the sine and cosine waves. So when I add those to the data, here I'm using the glimpse function to see what my data frame now looks like. In addition to count and time, I've got the different sine and cosine waves. That's sine wave 1, cosine wave 1, sine wave 2, etc. So I've got 4 of those, 4 sine and 4 cosine. It's a little hard to understand what they're doing, but it's basically like a basis expansion. So very similar to how we might set up a spline or something like that. So I'm just going to view some of these so you can get an idea of what these actually look like, which will help you to understand how they might be used for modeling repeated seasonal patterns in time series. So I'm just going to define some colors here, a vector of colors, and then I'm going to plot some of these. I'll plot, S1, 13, the first sine wave, and then I'll add to that, the first cosine wave, and then the second sine wave, and then the second cosine wave. So I'll just plot the first 2 of each of those so you can see what they look like. And here we can see that what we're doing is just expanding that into basically a basis expansion where we've got these repeated seasonal patterns or sine waves and cosine waves going at different kind of intervals. And so if we assign coefficients to each of these waves, those different weightings of those coefficients should allow us to capture a whole variety of different repeated seasonal patterns with just a few coefficients. So it's a really handy way to capture seasonality in time series. There are other ways we could do it as well. In fact, in GAMs and mgcv, which mvgam is kind of built off, there's a cyclic spline, a cyclic smooth function that you can use, which can capture repeated seasonal patterns as well. I'm just choosing to use the Fourier terms here so you can see a little bit about how we can estimate coefficients in a regression model in mvgam. Okay, so now that I've done that, this is all I'm going to need for this data set. I mean, mvgam, again, it's built off state space regression models, so you can have all sorts of predictors in your observation model and in your latent space model, in your latent process model. So you can have all sorts of covariates in there, and often that makes sense. That's one of the advantages of using mvgam over some of the traditional forecasting algorithms, like exponential smoothing, for example, which can't handle covariates very easily. Because we're trying to actually learn from those predictor variables as well to model a time series and to generate forecasts. But I only have these Fourier terms for now because I don't have any other covariates to use for this time series. And next I'm going to do something that's very common in time series modeling, which is just to split the data into training and testing splits. This is very often done. There are lots of different ways that you might want to go about doing this splitting, you might want to do this kind of iteratively, but it's a very common thing to do in time series models to both, you want to generate evaluations on your in-sample period, how well could you model the in-sample period, but because a lot of time series models are really flexible models, they can often capture the in-sample period incredibly well, just because they're really flexible. And it doesn't necessarily mean that they'll generate good forecasts. So we often want to compare models based on their forecastability as well, their forecast performance. That's very easy to do in a data frame like this, where we have a time variable. We'll just say anything less than or equal to time point 127 is the training data, and then we're going to reserve the last 13 or so time points for testing data for evaluation. Okay, so now I have a data train, which has 127 observations in it, and a data test, which has 13 observations. Okay, so that's everything we need to generate the model, and we can actually we can view this as well using mvgam series as well. So we can say data equals data train, and new data equals data test, and again y equals, I think we call it count in this case, and this will actually show you the split as well. So that's can be a useful way to see what is it, have I done that right, have I split the data appropriately. So it'll show you the training data and the testing data, and we can see what that kind of looks like here. So these are the data that we're going to eventually be evaluating forecasts on using some mvgam functionality. Okay, so now we're going to actually get into how to actually fit a model in mvgam. And there are many types of models that you can fit. It's a very flexible package, but I'm just going to showcase some of the functionalities today, and then I can point you to other resources in the help material below the video here to show you where you can look for a bit more information about how do you add bits of levels of complexity. But the first model we're going to fit is going to be a state space model. If you're not familiar with state space models, don't worry about it too much. Just understand what we're modeling is some latent true process, the true values of the time series, which we then take observations over the top of. They're really advantageous. For example, if you have missing observations, missing data, we don't think the time series just stops just because we couldn't observe it. It probably keeps going, and state space models can handle that. And they're really valuable because we can have predictors that we think influence the true time series, the latent state, but also predictors that we think influence our ability to take measurements of that true process. So you have two different formula arguments in mvgam models that allow you to capture both of those. Okay. Something that's very common to do, I think, are very useful to do in mvgam is to first look at the default priors. So this is a Bayesian, this uses a Bayesian inference. It uses the probabilistic programming environment STAN for estimation of these parameters using Hamiltonian Monte Carlo by default. Okay, which means we need to add prior distributions for a lot of the parameters of interest. mvgam can use a lot of functionality that's available in the brms package, in particular the GP function. If I go help brms GP, you can see a little bit about how that works. But basically, these are like smooth terms that you might use in mgcv, except they'll model nonlinear relationships as a Gaussian process. Okay. And we can actually account for all sorts of types of behaviors when it comes to nonlinear covariate effects using Gaussian processes, including nonlinear trends. So what I often like to do is decide on the model that I might like to fit, and then use get mvgam priors to look at what the prior distributions might look like, the default priors, and what priors am I able to change in this model. Okay, so the model that we're going to fit is something very simple like this. We have an observation formula, which is defined in formula, and we're just going to put an intercept in there. That's just the average count of this time series, the long-term average. And then in the state model, the latent state model, which is modeled using trend formula, we're going to have a Gaussian process of time. So we assume that there's some nonlinear trend happening in these data. And this is a zero-centered kind of latent trend. So we have no intercept in that one, but we have the intercept in the observation model. So nothing else going in this model. But again, you could have all sorts of levels of complexity in these formula objects. And all we need to do then is just pass the data and define a family, an observation family. So mvgam at the current time point can handle quite a few observation families. You can see that if we go help mvgam families, we can see a little bit about some of the families that it supports. It has some of its own families that are re-exported from other packages. But if you scroll down, you can see the current families that it supports. So a lot of families that are widely available in base R, Gaussian, Poisson, gamma, etc., as well as some other ones from mgcv and brms, beta regression models, negative binomial, beta binomial, and Bernoulli, etc. Okay. So we're going to use a negative binomial model in this case, which is very widely used for this kind of counts that aren't perfectly distributed. They might have a bit of over-dispersion in them. And that's just a good default one to use for count-based time series or any count-based data, because it can handle over-dispersion better than a Poisson could, but it can also collapse back towards a Poisson. We can estimate an over-dispersion parameter that allows this to behave very much like a Poisson anyway. So I'm just going to save this as DEF priors, get default priors, and you'll see we'll get a warning here, which is only displayed once per session. The default in GP is to set these arguments grouping equals true. In GP, if we go back to help here, we don't need to worry too much about that, but the default is true. That just specifies a behavior that mvgam currently can't use anyway. So if you set that to true, it'll just automatically set it to false for you, and it's just warning you here that that's been done. So you don't need to worry about that. It doesn't affect anything in the way these are estimated. And what we get back is a data frame that tells us a little bit about the prior information. So if I view that, I apologize for this being probably a bit small on your screen, but it tells us a little bit about the different parameters that are going to be estimated or that we're allowed to change priors on. There might be other parameters that we're not allowed to change priors on in some models. So we've got a prior on the intercept. We've got a prior on the over-dispersion parameter or the inverse of that. And we've got priors for the GP effects. So Gaussian processes often have a parameter for the marginal standard deviation, how much can it move up and down, as well as the length scale, which determines kind of how smooth or how wiggly the GP will actually be. Right, and very often with these models, you want to really pay attention to priors for the regression coefficients, because they need to kind of match what you'd expect to see based on the scale of your predictor variables. In this case, mvgam will do the same thing that brms does. It'll give you a sensible default for the intercept. So we often don't need to change that. This is actually uses a little bit of information from the data to give a more sensible default prior for the intercept. And often you don't need to change those. But often we do want to change the default prior on things like standard deviation parameters or any kind of scale parameter. And so the alpha parameter of a GP acts like that. How much can it move up and down? And the default prior is quite vague because the package doesn't really know how much you'd expect this thing to move up and down. Same thing for like sigma parameters in sort of normally distributed parameters, which we'll talk about again in a little while. So I often like to change priors on these. What we're defining here, again, is a negative binomial observation model. So that has a log link function. So all those priors are defined on the log scale. And so we don't expect a huge amount of movement on the log scale to be able to model the movement or the trend in this time series. It's not as if it's moving up into the thousands in counts. So often we can get faster fits with a lot of these parameters if we just change them to more sensible prior distributions. So when I define the model, which is going to use the mvgam function, everything else that goes into it is basically the same. I'm just defining an exponential covariance kernel for the Gaussian process. If you're using the very latest version of BRMS, you can actually use different types of kernels for the GPs, which is really useful. The exponential is the simplest one, which tends to fit the fastest. But by default, in the previous versions, was a squared exponential. So again, if I go down to help GP here, we can see the different types of kernels that can be used there. And in earlier versions, it was just this one, exponentially quadratic kernel, or squared exponential kernel. But I'm using the exponential instead, which is a little bit simpler and will just fit faster. It won't really make much difference. If you don't have the latest version of BRMS, that's not a problem. You'll still get very similar behaviors. But what I'm also doing is changing the priors. So the prior on that alpha GP, you can directly use the name. I'll go back to this just so you can see. You directly use this name here to change the prior of any parameter that comes from this default priors object. Okay, and so I'm just using that name directly to say I want to change that parameter, and I want to use a standard normal distribution. So standard normal in Stan, which is defined this way, this is in Stan language, tends to fit faster than just saying normal 0, 1. So it's just a computational trick that can make these a little bit faster. Okay, everything else is the same. So I'm defining the data. This is the training data. mvgam also allows you to supply the test data, if you like, at the time of model fitting. And what it will do is set these observations as missing and then generate predictions within the model for those. So we can actually generate forecasts at the same time that we're estimating those parameters. And that can often be a valuable thing to do. So mvgam, by default, will generate predictions for any data that it has. So we have actual, fitted values, hindcast predictions. But if we have new data in there as well, defined by the new data argument, then it will generate forecasts for you as well for that out-of-sample split. It'll use whatever covariate values you have in there, in this case, the Fourier terms, if we needed them, which we don't have them here. All we'll use is time in this case. But it'll use those to generate predictions, and I'm defining a negative binomial observation model. I'm also using some other tricks here. I'm not going to set this one yet. I'll show you how that works in just a moment. But I am changing the number of samples. By default, mvgam will fit 4 parallel Hamiltonian Monte Carlo chains, and it'll use the command Stan backend if you have that available and have that installed. So there's 2 interfaces to Stan in R. One is command Stan R, and the other one is rstan. So you need to have one of those available and working in order to use mvgam. By default, it's going to look for the command Stan R backend. If it can't find it, it'll use rstan. And that's just because command Stan R is a little bit more lightweight, a little bit faster, and more memory efficient, and more up to date than rstan. So it'll fit 4 parallel chains. We can use it if we look at help mvgam. We can see a little bit about it. Here's all the arguments. So the chains by default is 4 with a warm-up period or burn-in period of 500 iterations, and then 500 samples per chain. That's often more than enough for Hamiltonian Monte Carlo. It's not like the older Gibbs samplers that you need millions of iterations for. But sometimes taking more samples can be good just to get a better estimate of forecast distributions, and for model comparison that can be valuable as well. Okay, but everything else is the same in this case. All right, I'm going to fit this model. And what you're going to notice happens when we fit models in mvgam, first of all, we're getting a message here saying we might benefit from using non-centered equals true. So there's a way we can non-center a lot of state space models to get more efficient estimation. I won't go into the details of how that works, but you can read a little bit about that in the help documentation. Often it does improve sampling efficiency. But what happens is we'll get some messages. So this model is compiling using command Stan. So because Stan programs have to get compiled down to C++, you often have to wait just a little bit for the model file to be compiled down before it actually starts sampling. And so often there's a little bit of a lag time. People aren't necessarily used to seeing that. You're used to your models just going straight away. But in any package that uses Stan as the backend, like brms, for example, you often will need to wait for the compilation to happen. And mvgam is the same way. There's such a flexibility of models that this package can fit, that there's no way I could define a predefined model file that could handle everything I'd want to be able to do. And so we have to compile at the time of setting the model. So depending on the model, sometimes it might take very little time. Sometimes it might take longer to compile than it actually takes to run, because a lot of these models would run really quickly. And you can see here we're running 4 parallel HMC chains, and we're getting information about when they're doing warm up and when they're doing sampling. And then we get a bit of information about when they're finishing. Okay, so the first couple of chains are finished now. We're just waiting on that final chain, which is lagging behind a little bit. But you can see they don't take that long really for a full Bayesian inference of a time series model with a complex Gaussian process happening under the hood. 25 seconds isn't really too bad. And then what it'll do is calculate a few things to return in the object. Okay, and with any mvgam model, we can just inspect the summary, and by calling summary, so that's an S3 method that we can use. And one of the first things to look at is some of these diagnostics. Stan has incredible diagnostics that tell you a little bit about how the sampling performed. Was the sampler happy or not? Was it moving efficiently? We're getting some warnings here about some R hats that are a little too high, split R hat diagnostics, as well as some other warnings of divergences, which again, I can point you to resources to interpret what those actually mean. But all these are telling us is that the sampler wasn't running extremely efficiently. But in the summary, what we get is estimates, some posterior quantiles, and then R hat and number of effective samples of lots of different parameters. Here's the over dispersion parameter. So the larger this gets, as it gets into the hundreds or thousands, the model behaves more like a Poisson. If we get really small values, it captures more over dispersion. Okay, and here's the sigma parameter for the latent states. So the latent states evolve as Gaussian with their own process error, and this is the process error parameter in the state space model. And you can see that hasn't been estimated very efficiently. High R hat, very low number of effective samples. We also get estimates for all of the GP parameters as well as the intercept, and they all seem to have gone reasonably well. Even the alpha parameter has estimated reasonably well. But these warnings that we got before about non-centering might improve this model is worth looking at whenever you get these kind of models. If that message shows up for you in an mvgam model, then it's often worth trying it out. It doesn't help all the time, but in some cases it can help a lot. So all you have to do is say non-centered equals true. Unfortunately, that does mean the model needs to be recompiled because it creates a different model file. It's reparameterizing the model, but it makes it much easier to estimate those things like the latent sigma value and often the alpha parameter of a GP, for example. Anything that can capture kind of variation, excess variation, non-centering can help. And so I'm just going to set non-centered equals true and rerun this model. We'll have to wait just a little bit for it to recompile. Once that happens, it'll be worth checking to see what the diagnostics look like, whether they look better. Because very often what non-centering does is just make the same model a little bit easier for Markov chain Monte Carlo estimators to sample appropriately and to sample efficiently. So you tend to get similar estimates, but they tend to be have converged much better, higher effective samples, better R hats, things like that. So I'll just wait a moment for this to compile down, and then we can have a look at what this looks like. So mvgam, calling this returns an object of class mvgam. And there are lots of methods that you can use on objects of this class. So summary is one of those, plot and print, and a lot of the other methods that you commonly use in regression modeling packages. And we'll look at some of those in a moment. You can see this is estimated much faster. The previous one took about 26 seconds. This has taken about 8 seconds to run all 4 chains, and generally that's a good sign. If we call summary again, we can see down here we've just got a few divergences, very small number, and we could actually easily fix that by changing the adapt delta, which I won't go into detail with here. So there's nothing major to really be concerned about here. We can see that our effective samples are generally much, much higher for all these parameters. Even for the sigma, we're getting much better convergence in number of effective samples. And it's exactly the same model. It's just estimated more efficiently using some computational tricks. Okay, so in the summary, we get standard kind of output for a regression model. We get the formula objects for each, the observation and the process model formula, what family and link function, et cetera, were used, a little bit of information about number of process and series that we have. mvgam is really well suited to multivariate time series where you might have lots of observational time series, and you might even want to use dimension reduction, so you have fewer process models than you have observation series. So all sorts of things that you can do in the package, which I'll go into in later videos. So you'll get a bit of information about, the number of series you're dealing with. And again, you get information on all the actual regression coefficients, which can be a huge number if you're using things like splines or some GPs. You see lots of these coefficients. So the GP effects in mvgam are estimated using Hilbert space approximate GPs, which work kind of like basis function GPs. And so you get a coefficient for each of those basis functions. And often these aren't interpretable on their own. You can't really gain any information. You're not going to look at significance of any of these effects. They don't mean anything on their own. You have to use predictions from the model to really understand these effects, same as you would from any kind of generalized additive model. So mvgam has a conditional effects function that works directly on those model objects, which will show you some of those effects. And here we can see we only have one effect in this model, which is the temporal trend. And I'm saying I want to see the effect of that trend on the link scale. So this is on the log scale. And you can see here that it's clearly captured a nonlinear trend in this model. Okay, so if we wanted to, we could change this to say on the expectation scale. So type equals expected, and that'll show it on the actual count scale, not accounting for the uncertainty from the negative binomial observations, just like the estimate of the mean count through time, which is different from the link scale, from the log scale. Okay, we could also change this to type equals response to look at the actual predictions accounting for the negative binomial observation model, and that's going to have much higher uncertainty, obviously. Okay, so those are the various things that you can do with looking at effects. So conditional effects will return plots for all the types of effects, the main type of effects that you have in the model. So you have multiple coefficients in there, or multiple splines or GPs. It'll show you a plot for each one. Or you can be more targeted and use plot predictions from marginal effects to plot any kind of prediction plots that you want. So I'd highly recommend having a look at the documentation and from the marginal effects package to get an idea of how you can plot these models. This function plot predictions works on, I think, over 100 classes of model objects in R. So it'll give you consistent plots for many types of model objects, so really valuable. But all I'm doing is showing the same kind of thing here, where I'm showing predictions on the outcome scale and using type equals response, which is the default, and then overlaying the points as well on those. So this is what I would have predicted from my model against the actual observed values. We can also plot residuals using the plot function in mvgam using type equals residuals. So these are called randomized quantile residuals, but you interpret them in a similar kind of way. You expect them to be kind of normally distributed, and you don't expect to see any autocorrelation. And clearly we're seeing sort of a seasonal pattern of autocorrelation in these residuals, which suggests we need to account for seasonality in this model. Okay, there's other kinds of things you could do, but I'll again refer to the help files of the package to look more deeply. But for now, another sensible model might be to try and capture this seasonality that we're clearly missing when we look at these residuals. And so a way to do that is to, again, include the same GP. So we're using exactly the same model as previously, except now we're adding coefficients for seasonality. And again, I'm putting all of these in the latent space model in the trend formula, because I expect this is modeling the true actual process itself, Anything that I think affects how I observe that process, I would put up here in formula, which I don't have anything at the moment to go in there. So we're just literally putting the names of those variables in that data frame, and it's going to estimate one coefficient for each of these. I'm only going to use the first three rather than those four sine and cosine waves, just to keep it a bit simpler. I think that turns out to be enough to capture seasonality in this example anyway, but we could easily add all four of them if we wanted. Again, I'm changing the prior for the alpha parameter of the GP. I have to give it something more sensible, the standard normal, but I'm also changing the default prior for the regression coefficients. So the default priors for any kind of fixed effect coefficient in mvgam will just be a fairly vague student t prior. And I'm just changing that to a standard normal, a normal 0, 1, because that matches sort of the scale of the actual these actual Fourier terms quite well. So that will tend to estimate a bit quickly. So it's a much more informative prior, but not so informative that's going to influence what we estimate there. So you can wrap multiple prior calls using C in R, and it'll give you what we want. So if we just run that on its own, we can see what that gives us. It's basically a data frame with some attributes from brms package that tells it what kind of parameters we're changing. So that's a shortcut that you can use. That all regression coefficients for fixed effects are going to be given a standard normal prior. And then everything else is the same data, same new data. I'm going to stick with non-centered equals true in this model, and I'm going to run that model. So again, the only major downfall really here of anything that uses stan as the backend is that we have to compile every time we run a new model, and sometimes that compilation can be again slower than the actual estimation of the parameters. Sometimes it's really fast. It depends on how complex the actual underlying stan code is that's being written by the package. But the package internally it uses mgcv and brms to set up all the terms that we need and all the design matrices. And then it automatically writes the stan code for you. So you don't have to write the code in stan, and you don't have to be fluent in stan to be able to make these models work. There is a feature as well that you can actually view that stan code, which can be really valuable if you'd like to expand the models, get them to do something that the package currently can't do. You can set up all the stan code and the data that you need to fit the model, but not actually fit it, and then return the stan code and the data objects. And then it's up to you if you wanted to add other things to it, change things around, put multivariate priors on there or correlated effects that the package can't currently do, whatever. That's up to you to be able to do. So it should be very useful, I think, for expanding to much more complex kind of models. Okay, so this one's going to run, and you can see it's running very quickly. Again, very similar to the last one. All we're doing is adding these 6 coefficients in there for those sine and cosine waves. So that took 15 seconds to run, and now it's just summarizing. And then what we can do is, again, look at all these things. But I'll just show you the stan code as well. So if you use stan code for the model name, which is mod 2 in this case, and you can see the actual stan code that's automatically written by the package. All right, and stan models are defined in blocks. So you have a functions block, and there are functions we need to fit the Gaussian processes in this case, and some other functions as well. And there's a data block to specify all the fixed data types and their dimensions. And then there's a transform data block for transforming the data if you need to do that efficiently in stan, and then parameters for any stochastic parameters we need to estimate, etc. Right? So you can read about stan if you like. And again, you could easily modify this and already have all the data that you need. So we can use mvgam to give us all these data objects in a list and a model file, and then you can just make subtle changes if you wanted. Okay, but we're not going to go into detail of that in this tutorial. So again, if I call the summary, now I'm going to get those coefficients. My diagnostics look very similar to previously. So I've got all those GP effects again, but now I've got these sine and cosine coefficients, which again are not that directly interpretable on their own. I think you need to look at predictions from these models, but they've all sampled well and estimated well. You can use some Bayes plot routines in mvgam. So MCMC plot will call some Bayes plot functions. And I'm just using one to say any variable that has this pattern in it, which is all my sine and cosine waves, which you can see here. They all have that pattern. I'm just going to take any of those parameters that have that name in it using regular expressions, and I'm going to plot the posterior distribution of those. And you can see some of them are strongly negative, some tend to be more positive, and that's just capturing the more complex kind of seasonal patterns in the data. When we fit multiple models, we can use leave one out, approximate leave one out cross-validation to compare those models using the LU package. So LU compare will give us some comparisons based on the expected log predictive density. And here we want a higher value is better. So what this LU compare will do, same as in BRMS, the best fitting model based on the in-sample data will be at the top with all zeros, and then every other model that you have after that, and you can have as many models as you want in this function, will come below. And you'll get an estimate of how much worse that next model was in terms of ELPD, as well as an estimate of standard error around that. And we can clearly see that model one, the one without seasonality, was much worse, and that was consistently worse. We do get some warnings of high Pareto K diagnostics. For example, if I use LU directly on one of those models, you can see most of those effective samples were really quite high, and the Pareto K parameters were fine. We just have a very small number that were not so good. So I wouldn't tend to worry about that in this case. But again, you can read more about that and how that works by looking at the actual LU paper. If I go to help lu.mvgam, you can see a little bit of the details there on how that works, and it'll point you to the actual LU package itself, which will give you the primary reference of what's actually going on here. So this is a really common way to compare models by using approximate leave one out cross-validation. We can also look at predictions that have been directly sampled from the model. So again, we already calculated hindcasts and forecasts for this model, for both of these models. So we can plot the first model, which does not have seasonality, and all it has is the Gaussian process trend, and the next model, which has the seasonality. You can clearly see the difference in how they're estimating both the in-sample period, which is shown in gray, and the out-of-sample period. We do get some estimates of scores here as well, probabilistic scores, which I'll go into in a minute about what those actually mean. Finally, we can plot the residuals of this second model, and you can see the autocorrelation is gone. I wouldn't worry too much about patterns that you see in the fitted versus residuals. This will take a random sample of residuals because we've got 4,000 draws of residuals. So each time you run it, you can get a slightly different pattern in there, and often it might just be reacting a little bit. So I wouldn't worry too much about that one. It's more these kind of patterns of autocorrelation and clear, just differences from in the QQ plot that you're really more interested in looking at. You can also use posterior predictive checks in this package as well. There's lots of other ways you can assess model fit, but I won't go into details of that in this introductory tutorial. And finally, we can plot predictions the same way we did before using marginal effects, and we can see that it's clearly capturing the seasonal pattern. So it's a fixed seasonality. Because of the log link, the seasonal pattern grows as the sort of trend grows, so it's a multiplicative seasonality because of that log link function. But the overall shape of the seasonal pattern doesn't change over time. So an obvious thing to think about would be, well, what if we allowed that to change over time? And we can do that very easily with GAMs. We can set up the same kind of model as before, but instead of fixed effects of those sine and cosine functions, we can actually use bi terms, the bi variable. And you can use this in a spline using S. So I could replace that with S. It would almost work the same way. But I'm going to do it with GPs as well, just to show you how that works. So what this will do is fit a GP of time separately for each of these coefficients, but then it's multiplied by the value of that Fourier term And so basically what it's fitting is a time-varying effect, time-varying coefficient for each of these sine and cosine waves to allow the seasonal pattern itself to change over time. I'm using a very small k value to restrict these so that they can't change too quickly, because I don't expect that seasonality would change too fast. Okay. But again, that's what this is allowing us to do. And you can look, there's lots of useful examples about bivariables in mgcv. I think it has a whole help file actually on bivariables and how you can use those. And the same kind of process works for these GP terms. So these are time varying effects. And I'm doing that for each of those sine and cosine waves. I have a blog post on these as well, which I'll link to in the information below this video. So you can read in more detail about how this works and how you could use this even to capture time varying periodicity if you wanted to. But for each of those GP effects, I'm actually resetting the default prior, again, using a standard normal for their alpha terms. So each of these is a separate GP. So they each have their own parameter to capture that marginal variation of the GP. How much can it move up and down, or in magnitude? And the default prior will again be some wide student t that doesn't make sense on this log scale. So I'm resetting all those to standard normal. Okay, and that's all I'm doing in this model. So it's very similar to before, except these are allowed to change over time. It'll take a little bit longer to compile this one because of all these GP terms. They just take a little bit of time, not much, but a little bit of time to set up behind the scenes. And then the model file is just bigger, so it takes a little bit longer to compile down. But these can be really valuable time-varying effects. You can do the same thing over space. So you can easily fit GPs or splines where you have two covariates in there. So I could have a spline that has latitude and longitude, and then a bi term for some other covariate that I think the effect of that covariate changes smoothly over space. So spatially varying coefficients, other types of time varying coefficients you can easily model in this package because they're so easy to handle in both MGCV and BRMS. Okay, so there's a huge amount of flexibility again that you can put into this modeling package. But what I'm walking through here again is a standard kind of workflow. We start with a simple model, just a GP of time, that's it. And we saw there was seasonality in the residuals, which we already kind of expected to see anyway. So we added a little bit of complexity to the model with fixed seasonal coefficients. We investigated both of those models, looking at how well did they actually estimate. We're changing priors in a useful and targeted way. And then we're adding in complexity again here by allowing the seasonality to change slowly over time. But in none of these models are we just jumping drastically between models. You can do that if you have a set, space of models that you want to fit. But very often in an iterative workflow, we work like this. We start simple and then we build up, especially with complex Bayesian models where lots of things can be happening, which you might not expect. Or might not be that clear without, first fitting the model and then seeing what happens from there. So I highly recommend with any models that you're fitting, start simple and then build up in complexity from there. This model can be, it's reasonably complex. It's got quite a few Gaussian process effects in it, as well as the other things that are happening. Okay, you see it fit very quickly again. The advantage of these approximate GP effects, they fit really fast. All of our diagnostics look again the same. We could remove these if we wanted to. It just makes the model run slightly slower, but I'm not going to worry about them too much here. But what we've got in addition to what we had previously is all these other effects. There's a way you can suppress a lot of those the actual GP coefficients and spline coefficients called include betas equals false, which will only give us summaries of the main effects in the model. This is often really valuable if you've got hundreds and hundreds of coefficients in there, which we'd have many, many of in this model. Again, none of which we can directly interpret anyway. So I recommend doing that just to get a simpler summary output. So again, same kind of output comes from this summary, much more complex formula objects than before. But now we're just looking at the alphas and the row parameters for each of those GPs, just to make sure that they've converged reasonably well. Okay, I'm just going to quickly plot the residuals to see. They should look roughly very similar to what we saw before. Okay, not much autocorrelation left to worry about. And if we just run through plotting predictions again, we can see that the seasonal pattern does change slowly over time in this model. It's not estimating the same kind of predictions as we saw in model 2, which I can quickly show you if we bring that one up here and look at model 2. You can see they're slightly different between the two models. There's model 3 and model 2 there. We can also use, as I mentioned, the Gratia package for looking at effects from these models. So this works really well with mgcv models, GAM objects. It also works in mvgam. We have to call trend effects equals true when we're calling this draw function from Gratia, because these are all happening on the latent trend formula. And that just gives us nice plots of some of these smooth terms or GP terms. So here we've got the long-term trend, and these are all on the log scale, on the length scale. But we can see the time-varying coefficients for some of these sine and cosine wave functions. So this one tends to be mostly negative, as we saw before in the first model, but there is some evidence that it might change slowly over time. And some of these other ones change a little bit over time as well. Some of the other ones don't tend to do much, but this kind of change over time is what allows that seasonal pattern to change slowly over time. There are ways we can inspect that further as well to actually look at the time-varying seasonality. There are lots of types of predictions we can do from the model. So I'll walk through this code very quickly, but basically I can predict from the model by conditioning on time, and just to get the smooth trend itself. So that's going to take the average effect of all the seasonal patterns, just to look at the long-term trend. And then what I'm going to do is get seasonal predictions as well as the long-term trend predictions, and take the difference from those. So now I'm going to end up with effects that are only capturing the seasonality. Okay, and again, I go into more detail of this in the blog post, which I'll link to below on how this actually works. But basically, I get a second plot that allows me to look at the time-varying seasonality with the trend removed. And we can see what's happening in this model, how it's actually being decomposed to capture the patterns in the data. Right, here's the seasonal pattern that's slowly changing in shape over time. It's trying to capture this kind of second blip that tended to occur a few times later in the time series, and seemed to be kind of consistently happening. Okay, and not a lot of modeling packages are going to allow you to capture these kind of effects. Again, if we compare based on in-sample comparisons using LU-compare, it turns out that this third model with time-varying seasonality does tend to fit a little bit better. It's a little bit more strongly supported, although that the difference is a little bit uncertain how much better it fits the data than model 2. So, but both of these models tend to be performing much better than the first model that didn't have seasonality in it. And again, if we plot the forecast, we can see the first model with no seasonality looks like that. Second model with fixed seasonality looks like that. And the third model with time-varying seasonality looks like this. And interestingly, you can see, even though that third model was giving us the highest in-sample predictions, it actually gives the worst probabilistic score, the worst forecast score. So it performs worst of these three models on the out-of-sample. And that's very common with time series models. That's why we don't want to rely too heavily just on in-sample comparisons when we're choosing among models. We kind of need to weigh both of those up if possible. And it's really because that second kind of blip in the seasonal pattern, which was showing up a few times earlier on at the end of the time series, that didn't really seem to happen in the out-of-sample period here. I'll just zoom in so you can see that a little more clearly, how this model is kind of missing something. It expected to see an extra jump here, but the counts tended to be quite low. So that wasn't really happening in that out-of-sample period, which is why this one doesn't fit as well. A very final model that I'll fit is just to say, well, what if we replace that Gaussian process with a more traditional kind of time series model, and we'll use a random walk for that. So mvgam can handle autoregressive processes as well as random walks. And I'm just going to stick with the fixed seasonality here and replace the Gaussian process with a random walk. And you can just call that using trend model equals RW in mvgam. And you can read about that, help mvgam RW. You can read about how these things actually work. There's lots of things they can do for multivariate series, but for a univariate series like this, we just call RW, and that's all we've got to do. All right, so I'll call that one quickly. That one won't take as long to compile because it's a simpler model. But then we can compare that model as well, just so you can get a handle on what these actually look like with a totally different kind of idea about how the temporal trend evolves. Okay, so that'll take a second to compile and estimate. Random walks can be hard to estimate sometimes because they can be non-stationary. They're by default non-stationary time series models. So often you might want to use an AR1 if you're instead of a random walk, but it kind of depends on what series you're modeling and what kind of behaviors you expect to see. I'm just fitting in a random walk in this case just as an illustrative example. I don't actually expect that model would be necessarily better for this time series, but for many series they might perform really well. And so in mvgam, you can have very simple models that just have a random walk as your latent process and nothing else, just the observation model. Okay, we see that one running quickly now, and it'll be finished in just a second. So all these models are generally tending to take about the same amount of time to fit, even though they vary in complexity. So that's encouraging to see from these data. Okay. So I'm not going to bother looking at summaries of this one. I just wanted to show that as an illustrative purpose of how you can fit more traditional time series kind of models, random walks, and autoregressive processes as well in this package. Again, we'll use LU-compare. I tend to discourage using LU-compare too much for models that have flexible processes like AR1s or random walks, because they estimate a parameter for every time point for every series. So they're a little bit harder to approximate these. If we have a look at LU for mod 4, we'll tend to see, in this case, it performs fine, but often we'll tend to see a lot more of these estimates being bad or very bad. This one seems to be okay, but very often that does happen. But in the LU-compare output, we can see that model 4 is performing very similarly to model 2, these are both the models that had fixed seasonality. Model 2 had a Gaussian process for the trend, and model 4 had a random walk for the trend. And we can see what those tend to look like. We plot model 2 again. Here's the Gaussian process with fixed seasonality. And we plot model 4. Here's the random walk. And they look pretty similar. Maybe the uncertainty grows a bit more in the random walk. But both of these will tend to extrapolate kind of flatly ahead. The GP can extrapolate nonlinearly ahead if there's enough information in the covariance, but the random walk will always extrapolate flatly from these, and the uncertainty will grow pretty quickly. And you can see that they both have very similar probabilistic scores. So on that note, a final thing that's often worth doing with time series models is to build ensembles. If you have multiple models and you're not sure which ones to use, your in-sample metrics favor one model and your out-of-sample favor a different model, sometimes it's worth just putting all those together and giving an ensemble forecast. So mvgam has ways of doing that. We can use the forecast function to pull out the actual forecasts from each of these models, which I use here. And what's returned from these is an object of class mvgam forecast. And that has methods available for plotting and scoring forecasts if we wanted to, but also for ensembling. So the ensemble function in mvgam will just take forecast objects, any forecast objects that you want, as long as they cover the same data and the same time periods. But they can come from any different types of models, and it'll create an evenly weighted ensemble from those forecasts. So if we run that, what we get is our best ensemble from all 4 of these. And very often these tend to perform better than any individual models on their own. In this case, I think it performs slightly worse than the random walk, but better than the GP and better than either of the other models as well. You can directly evaluate that by scoring these. There's a score function in mvgam. So if I were to score that first forecast, for example, SC1, you can set the score type. In this case, we'll use the discrete rank probability score. And what that returns is a list object that gives you scores for each series. There's only one series in this object. Where you get the actual score, whether it was in a certain interval width, as well as the forecast horizon and the type of score. So these are meant to be in a format that you could easily add lots of these together in a tidy sort of format and plot those in ggplot. But if I just sum up those scores from a couple of those models, here's the sum of DRPS for the out of sample for that first fixed seasonality model with the Gaussian process, and then with the random walk here, which was slightly better, and then the ensemble, which is kind of in between both of those. But very often the ensembles will tend to perform better. Okay, there's lots of other information you can get on mvgam models. This is just meant to be a sort of a simpler introduction to the package and some of the things that you can do. But I really appreciate everyone listening and would welcome any feedback that you have on other things that you'd like to see. I'll be expanding this series of introductory tutorials to talk about some of the interesting things that I think you can do in the package and other sort of directions for future use. Okay, but thanks everyone, and please give a like if you found this useful, and I look forward to hearing from you again soon.